Waves. We're going to get right into it. As always, if you enjoy this content, give us a like and subscribe. So before we talk about waves, we need to define what a wave is. And a wave is an oscillation or a vibration in which energy is transferred between points. Now, there's a key point here, which energy is transferred but not mass. It's very, very important to know that, okay? So energy is transferred, not mass. And we'll talk about the way that this happens in more detail as we move along here. But for now, what's a vibration? What's an oscillation? It's just a motion up and down, or left and right, or it could be at an angle like this. But the key idea is that it's a back and forth or an up or down. Now, when we talk about oscillations and vibrations, they take time. And this is our first key concept in waves, which is the time that it takes for a vibration is called the period. So the period is a time, but it's a very specific time. So the symbol is a capital letter T, and that's period. And because it's time, it's measured in seconds. So what is period defined as? It is the time to complete what? Well, we could say this a whole bunch of different ways. The time to complete one cycle, oscillation, vibration, and we could even define it mathematically as 360 degrees or 2 pi. So it is the time to do one of these, and these are all the same thing. Now, frequency is related to this, and frequency is defined as the number of cycles completed in 1 second. So that is the number of cycles. Now we say cycles, but it could also be oscillations, vibrations, 360 degrees, or 2 pi. But usually the word cycle is used when we're talking about frequency. So the number of cycles completed in 1 second. And if we're doing this in 1 second, then we use a unit called the hertz. And hertz is abbreviated Hz. The formula for this, which is on the reference table, is T equals 1 over F. The period is equal to 1 over the frequency. But we can also cross multiply and write this formula as F equals 1 over T. These are two acceptable ways to write this same formula. To get a better understanding of these two variations of the formula, let's go ahead and solve a problem. Let's say we have 10 wave crests passing a point in 5 seconds. Find the period and the frequency of this wave. So when we say wave crests, a crest is the distance from the peak of the wave to the next crest, and that we'll learn later is called the wavelength. The wave crest is going to be, from crest to crest, is going to be 1 cycle. So that right there is our cycle. That's our oscillation. And from math, you should know that that's 360 degrees. It's a full wavelength. Or in math, you also define that as 2 pi radians. So we have 10 wave crests passing a point every second. So we can say that we have 10 cycles, in 5 seconds. In 5 seconds. Well, let's divide that and get a number. 10 divided by 5 is 2. Cycles per second is hertz. So we've done our equation. That's our answer. 2 hertz is our frequency. Now, if we want to find the period, all we have to do is take our formula. F equals 1 over T. So we have 2 hertz equals 1 over T, and cross multiplying, we can get T is equal to 0.5 seconds. So let's go back and look at what these two things are saying. This is saying that the frequency is how frequently the wave is oscillating. This is about the vibration. It's going up and down 2 times in 1 second. This is saying the time for the full cycle to go by is 0.5 seconds. So let's go ahead and draw out a wave so that we can see exactly what's happening. We would say the time it takes for this point P right here, for this crest to get over to where this crest is, that's going to take 0.5 seconds. But when we talk about the hertz, what we're talking about is this wave is oscillating up and down. It's going to do that 2 times in every second. That is 2 hertz. This image shows one small portion of our night sky as viewed from the Hubble telescope. Within this image, we see multiple galaxies, each composed of roughly 100 billion stars. As vast and mysterious the universe may seem, it is governed by fundamental concepts. For example, the vibration of electromagnetic waves, such as light, X-rays, and ultraviolet, travel across our universe and do so according to an oscillation called simple harmonic motion. Simple harmonic motion can help us to understand our universe on the galactic scale and all the way down to the atomic scale, as we see here in the vibration of a CO2 molecule. Simple harmonic motion occurs when a restoring force, such as in a spring, is directly proportional to the displacement of an object. So the condition for simple harmonic motion is that the force is directly proportional to the displacement. An excellent example of this is a mass on a spring. The greater the displacement from equilibrium, the greater the force. So the maximum force occurs at the high and low points where the spring is most compressed and most stretched. And the force is 0 when it passes through equilibrium. Simple harmonic motion in a spring exhibits wave motion. If we imagine the oscillator moving through space, a wave is produced. Even circular motion and pendulums can act as simple harmonic oscillators. If we rotate an object that's moving in a circle, we can see its motion viewed in 1D resembles that of a mass on a spring. So circular motion shows simple harmonic motion. Here's a pendulum oscillating back and forth. Just as with the spring and circle, we can see that the motion of the pendulum exhibits simple harmonic motion. By rotating our view, we can see how this resembles wave-like behavior. We've now seen how simple harmonic oscillators can produce and exhibit wave properties. The 3 types of harmonic oscillators are the mass on a spring, an object rotating at a constant speed in a circle, and the pendulum. We will use the pendulum to explain the fundamentals of wave behavior, which include period, frequency, and amplitude.
A pendulum swinging back and forth is a wave-like behavior. Today we're going to use a pendulum to demonstrate 3 fundamental characteristics of waves: period, frequency, and amplitude. Period is defined as the time it takes to complete one full cycle.
And a cycle is when you go from here all the way out here and all the way back again. And that's one complete cycle.
Again, period is the time it takes to complete one full cycle. We can use a timer to measure the period of Miss Bates.
This amount of time is the period.
Period.
Okay, so we shorten the rope. Let's see how that changes things.
Yeah, with
ready?
a shorter rope, let's see what the period is this time.
Okay, are you ready? Not
Ready.
when those guys are there. Alright, here we go. Whoop. Oh wow, that was a lot shorter.
Yeah, your period is only 3.5 seconds with a shorter pendulum.
Okay, so what does that mean? Shorter time means...
That means the frequency will be greater. You'll complete more cycles per second.
Alright, let's figure that out.
Let's calculate and see if that's true.
The period of Mrs. Bates was 3.5 seconds. That is, the time it took her to go there and back again. We now want to know how many times or cycles she completes in 1 second, and this is called the frequency. Since period is the time for one cycle, and frequency is the number of cycles in a time period, we say that the period is the inverse of the frequency, or T equals 1 over F. To calculate the frequency, we put the period into the formula and take its inverse. You can do this with the 1 over x or x to the minus 1 button on your calculator. Then all we need to do is box those puppies up. So, as the pendulum length decreased, so did the period. But as period decreased, the frequency increased.
Alright, I think we got it all.
Yep, we're all set.
Alright. Oh, we forgot to do amplitude.
Oh yeah, we forgot about amplitude.
Alright, why don't you tell them what amplitude is?
Amplitude is how far a pendulum swings from equilibrium. It's a measure of maximum displacement.
So, here I'll have a small amplitude. And that.
That time you didn't swing very far from equilibrium.
No, but here I'll have a big amplitude. Woo! Now that's a big amplitude.
For a mass on a spring, the maximum displacement occurs when the spring is most compressed at the top and most stretched out at the bottom. So amplitude is the maximum displacement from equilibrium. For a pendulum, equilibrium occurs at the bottom of the swing. So the amplitude is the displacement from equilibrium to the maximum height, which occurs on either side.
Alright, that's a wrap.
Yep, I think we're all set. Oh, we forgot to tell them what the unit for frequency is.
What, the unit for frequency?
Yeah.
Ow! Ah! That really hurts!
Oh, I think he needed to hurt.
Oh! Yeah.
Are we done?
I think so.
Did we not remember this conversation? Are you pulling? I'm
Yeah. Okay, you can go now.
Go where?
Like, let go. Go out and just
I'm gonna
swing.
swing back against a rock.
No, you're going to swing this way.
Conservation of energy.
Don't you teach physics?
Yes, if I go there. This is the real world, though. Remember the whole physics land deal we had?
All right, go ahead.
I'm not.
That's it. Now go off the rock.
Can I sit down?
Yeah.
Yeah.
Oh my god! I can't get back up on this stupid rock.
Well, Joel can grab onto you.
Yeah, Joel's just sitting there.
Okay, perfect.
Christian, I'm not
red.
Joel.
The red dot's
I'm not
there.
going.
Yeah.
I'm not. You're gonna knock the rock down. Christian, no. This is just so unsafe. And now what happened? Now we're stuck here. Good job.
Yeah, we're stuck here forever. So here's a new vocabulary term. It's propagation. Propagation is the direction of the energy travel in a wave. So let's say we have a wave like this. So this is like a sine or cosine curve. So if the wave is propagating, what that means is as this wave is moving along, it's really only the energy that is traveling, and it is traveling, in this case, to the right. That would be the direction of propagation. This is called a transverse wave. There are other types of waves. There are longitudinal waves, and these are made up of things called compressions and rarefactions. So if you can think of a slinky, and at one end of the slinky we push it, some of the wave gets scrunched up and some of the wave gets spread out. The scrunch up part is our compression, and our spread out part, that's called our rarefaction. So in this wave, we can think of this as our crest and our crest. We can also think of the center of the compression to the center of the compression as our crests. Now, we don't use the word crest, we just use the words compression, but that's the distance between one cycle. It's actually also our wavelength, which we'll define later. So we could have a wave that's compressing like this, so the vibration is this way, but the energy is traveling through the wave down in this direction. So in both of these cases, we have the waves propagating to the right. That means the energy is going from here over to here. We could have the wave go in the other direction, in which case the energy would be starting here and ending over on this side. So propagation can be in either direction. What if we only have one disturbance? Well, that's called a pulse. So a pulse is a single vibratory disturbance. So what does that mean? Well, if we're talking about transverse waves, then we're talking about just a single vibration that is traveling through space. So this one vibration by itself is moving along, this is called our equilibrium position, along a rope, through the water, or whatever medium it happens to be traveling through. If we are looking at a longitudinal wave, which is a compression wave, then a pulse would be only a single compression that is propagating through the wave. So there are some important definitions here then, and that is, what is a longitudinal wave? Well, a longitudinal wave is one in which the wave vibrates parallel, and this is the key word here, parallel to the propagation. So if we look at this example right here, this compression is compressing left and right, but the propagation is to the right. So these two are parallel to each other, so therefore this is a longitudinal wave. When we talk about transverse waves, then we have the opposite situation. In a transverse wave, it's a wave that vibrates how? Well, what's the opposite of parallel? That would be perpendicular. So it's a wave that vibrates perpendicular to the propagation. So again, we can look at a wave that looks like this, and we say it's propagating this way and vibrating this way. These two are perpendicular to each other, so that makes that a transverse wave. And remember, in both types of waves, it's only energy that's transferred, not mass. Amplitude is another wave characteristic, and it's defined as the maximum displacement of a wave from equilibrium. And it's the absolute value, meaning that if we measure the distance up, and that ends up being, we'll make up a number, let's say 1 meter, and this is down 1 meter, we would say this is -1, but that doesn't mean the amplitude is any less. So these two amplitudes are equal. We take the absolute value. This position right here is called the equilibrium position. So the equilibrium is just this line that goes through here, and the distance from equilibrium to the top of a crest, or from equilibrium down to the bottom of a trough, these distances are the amplitude. And this is what tells us the wave energy. So the larger the amplitude, the stronger the wave. And if we're talking about light, that would be brightness. And if we're talking about sound, we're talking about loudness. Now, this type of wave is transverse. So this could be light. But sound waves are longitudinal. However, sometimes we represent, even though this is a sound wave, we represent our sound waves this way because there's a nice way to look at the amplitude. But don't get confused, sound waves are longitudinal, electromagnetic, which includes light, are transverse. Now, when we talk about wavelength, wavelength is 2 pi, or we can say 360 degrees, and this is the distance of one cycle. Now, we can define this as crest to crest, so that would be from here over to here, and that would be one wavelength. The symbol for wavelength is the Greek letter lambda, and because it's a length, the unit is the meter. Now, we can say from crest to crest, but the bottom of the wave is called a trough, and we could also say from trough to trough. That's one wavelength. But it's one cycle, so it could also be, in a sine wave, it could be this distance from here all the way over to here. So that's one wavelength as well. Or we could say from here and go through one full cycle, and that's also a wavelength from there to there, 360 degrees. So let's just be careful and make sure we know how to break up our wave. This is one full cycle. So this right here is 360 degrees, or 2 pi. If we cut the wave in half, then this distance right here is 180, and from here to here, that's also half of the wave, so that is 180 degrees, or we could say pi radians. If we chop this into quarters, then this distance right here is 90 degrees, or we can say pi over 2. How do we calculate the speed of a wave? So we know that our formula for speed, when we're talking about constant velocity, that's v equals d over t. Well, let's do this for a single cycle. If we're doing this for a single cycle, the distance of the wave would be one wavelength, so that's lambda. And the time for one cycle becomes the period. And we know that period is t, so we can replace that with 1 over f. If we multiply through by f over f, that's going to cancel these f's, and we're left with a new formula that is v equals f times lambda. Now, there are a lot of questions that use this formula, but occasionally you can still use this formula if they give you the distance and the time for the number of waves to travel through that distance. So the frequency we know is in hertz, and we know that the wavelength is measured in meters, and that's cycles per second, and this is meters for one cycle. So cycles will cancel, and we'll be left with meters per second, which is what we would expect. So putting this formula into practice, let's say we have a radio wave. Now, a radio wave is electromagnetic, and it is transverse. But we don't need to do that, or even know that, to be able to solve this problem. So we have a radio wave that has a wavelength of 1.3 times 10 to the 2 meters. What is its frequency? Well, we can just do v equals f lambda. And what is our speed? Well, radio waves are electromagnetic, which means they travel at the same speed as light. So if we look here, speed of light in a vacuum, that is 3 times 10 to the 8th meters per second. Had it been a sound wave, we would say speed of sound in air. We would have used this number, 3.31 times 10 to the 2. But we're dealing with a radio wave. Radio waves are electromagnetic, and they travel at the speed of light. So we put in our 3 times 10 to the 8th meters per second is equal to f times 1.3 times 10 to the 2 meters. And if we do the math on that, we end up with a frequency of 2.3 times 10 to the 6th hertz. Now, sometimes they aren't going to leave the unit that way. They'll ask you to put it into a scientific power of 10. And we know that 10 to the 6th is mega. So what we can do is rewrite this as f is equal to 2.3 megahertz. The principle of superposition is a lengthy definition, but the concept is actually much easier than it sounds. But let's go through it first. The principle of superposition says that when we have two or more waves interacting, okay, so two waves, in this case we're going to deal with pulses first, and then we can look at full waves. So pulses or waves interacting in the same medium at the same time. In other words, they're crashing into each other. That's all that means. And they're doing this at the same time. They produce a new wave equal to the sum of their amplitudes. So let's say we have this situation. We have a pulse, which is a wave, traveling to the right. It's propagating to the right. Its energy is traveling this way. It's vibrating this way. And we have another pulse propagating to the left. Well, they're going to crash into each other. And that's where the principle of superposition takes over. The amplitudes add up. So if we have 2 meters and 1 meter, the new amplitude is 3 meters. So this is what happens during superposition. Now, if this wave had been -1, like we had a pulse down here, then we would add the negative, and that would produce a smaller amplitude wave of only +1. What happens after superposition? What happens after these waves crash into each other? Well, nothing really. They just continue to move along as if nothing happened. So the wave characteristics remain the same. Okay, we have two different pulses here. We have a positive amplitude pulse and a second positive amplitude pulse. And what we're going to see is these two pulses crashing into each other, and that's going to be the principle of superposition. So we can see they approach each other. As they superpose, the amplitudes add to produce a new pulse, and then they move on their way in the opposite direction. Now, if we are to reload this for a second and we let this replay, then what we can do is pause the animation right at the maximum point of superposition, which is right there, and the sum of the amplitudes of these two pulses is going to be equal to the amplitude of this pulse. Let's look at another animation. In this case, we have one of the pulses has a negative amplitude. What's going to happen when they crash into each other? Well, we're adding the negative, so effectively we are subtracting the amplitude, and we'll pause this when this gets right over the top. Because these amplitudes are equal and opposite, they'll completely cancel each other out, and we should just get a straight line, if I can do that right there. In this situation, we are going to have two complete waves, not just pulses. So you can see that as these approach each other, right here we have a crest, and that crest is going to crash into this trough. So what's that going to look like when they interact? Well, this happens pretty fast, so let's just go back a second here. And we can see that from here, the first thing that's going to happen is this crest is going to cancel out with that trough. So that's going to make a smaller amplitude wave. So it looks like that. There, and then it's flat. But as it progresses, then that crest is about to crash into this crest, which is going to produce a larger wave, and we get a trough crashing into a trough. So the full situation of two waves that are, in this case, they oscillate between out of phase and in phase, are going to cancel and then produce a larger wave, and that is our result. We can look at another situation here where the two waves start out as crests. So what's going to happen when they crash into each other? Well, we're going to get positive superposition first, so we get that larger wave, and then the crest and the trough are going to cancel, producing nothing, and that's going to oscillate back and forth the same way. Let's apply the superposition to two different waves that are not in phase, and they also have different amplitudes. So how would we get the new wave from this? Well, the way we would get the new wave is we would add up the amplitudes at each position. So for example, I just drew a dotted line here to see where these are lined up. Well, at this point, we have wave 1 has 0 and wave 2 has 1. So we would add up and put a point there for 1. And then at this point, we have 2 and negative 1. So at that point, that would leave us with positive 1. And then here we have 0 and about 0.5. And then here we have negative 2 and plus 1, so that would be 1. So our wave here would look like that. If we have waves that aren't necessarily sine waves, we could have something like this, where we have a square wave and a triangle. What those will look like when they cross each other would be something like this. After they pass through, this wave would be on the other side, and this wave would be on the other side of it.